Our next speaker will be Fatemeh Rahmanifard, who will talk about hysteresis in the galactic cosmic ray variation and implications for future solar activity. Perfect. Okay, we can see your slides. So please take it away, Fatemeh.
Hello all, I'm Fatemeh and I'm a research scientist at the UNH Space Center. My primary focus of research is the effects of solar variations on our space environment, more specifically as a creator, LRO, and leader survey team member. I am interested in the GCR's radiation and how it limits crewed space missions due to the recent decline in solar activity. This study has been submitted to Space Weather, and here you can see the name of my co-authors. The flux of GCRs is constant at the interstellar medium. Inside the heliosphere, GCRs are modulated by the heliospheric magnetic field, HMF. The flux of GCRs reaches its maximum during solar minimum when HMF is too weak to modulate them, and the modulation potential is defined as the energy lost to GCRs as they travel from the edge of the heliosphere to the inner heliosphere. It can be used to describe the interaction between the GCRs and the HMF or the solar activity. In a recent paper in 2020, Rahmanifard et al. Paper, we investigated the correlation between the modulation potential from crater, as you can see the plot here, with solar wind parameters. Here, phi is the modulation potential based on crater data. V is the solar wind speed from Owens et al. 2017 paper, and B is the intensity of the heliospheric magnetic field from our 2017 model. As you can see here, we use a color code that darker data points are associated with the beginning of the solar cycle. And as we proceed in time, the data points become lighter. So you can see the hysteretic behavior in this correlation, which motivated us to further investigate these correlations. While crater data only covers cycle 24, we can extend our analysis to previous cycles using the results from Badwar-O'Neill 2014 model. So we get the modulation potential from this model, and we use again our model and Owens et al. Model to get the solar wind parameters. And we extend our analysis back to the previous 24 solar cycles. You can see in this figure and in the table, we have separately shown these trends that we have observed in these correlation diagrams for even and odd cycles. We are actually looking for trends that could be used in the prediction of future solar cycles. So in the first row, you can see a steep increase, and again we use the same color code. We use darker data points for the beginning of the cycle, and they become lighter as we proceed. So in the first row, we can see a steep increase in the first half of the cycle and a more gradual decrease in the second half. Is indicative of a weaker next cycle. The opposite trend is shown in the second row, where a more gentle increase in the first half and a sharper decrease in the second half represents a stronger next cycle. When the difference between the slopes of the two halves aren't that significant, it leaves the next cycle inconclusive. As you can see in the table, we show the schematic figure of these trends along with the list of cycles that represent these trends. And among the 11 cycles for which the diagram, the shape of the diagrams are conclusive, we can successfully predict whether the next cycle is weaker or stronger for 9 cycles. There is a well-known correlation between the minimum of solar activity and the subsequent maximum solar activity. Here we have shown this correlation with B min and B max. Again, B is the intensity of the heliospheric magnetic field. And you can see we show a fairly good correlation here. But what's new in this, and this has been studied in previous several studies. Jody Wilson also has a poster. It was actually, his poster was yesterday, where he showed a remarkable correlation between the amplitude of solar cycles and their previous minimum solar activity between the sunspot numbers. And he actually, in his study, he shows like a significant improvement to compared to previous studies. But what we have here is in terms of the heliospheric magnetic field, and what we show in addition to the previously known correlation is that we show these data points with the blue X that are associated with our predicted weaker cycles. And we see that they mostly fall below the correlation line. The red X shows cycles that we predict to have a stronger next cycle, and they are located above the line. So this suggests that these correlation plots reveal a physical effect in addition to the correlation between the amplitude of cycles and minimum solar activity observed before the cycle. So furthermore, the correlation diagrams in this study, together with this correlation, B min and B max correlation for the inconclusive cycles. The inconclusive cycles here are shown with the gray data points, and you see that they show a much stronger correlation after removing the data points that are marked with the red and blue X. We see a much stronger correlation. So this correlation for the inconclusive cycles, along with the correlation diagrams that we presented earlier for cycles that actually predict a stronger or weaker next cycle, together form a tool to predict future solar cycles during the ending phases of the current cycle. Based on this analysis, we predict cycle 25 to be as weak as or weaker than cycle 24. This might suggest that the sun has entered a secular minimum, which based on historical records might stay for another 2 solar cycles, cycles 25 and 26. This means that while solar maxima are known to be safer from GCRs, the next lunar mission will encounter higher GCR fluxes than did the Apollo missions. And I finished that here. I'll be happy to answer any questions.
Okay, thank you, Fatemeh.